Okay, something related but slightly different is diffraction gratings. Okay, so far we've just looked at things going through a double slit, so two uh, pieces of two waves basically. It could be coming from one source, but then getting split into two by looking at through two slits. Okay, so a double slit gives a very dim interference pattern, since very little light can pass through the two narrow slits. Using more slits allows more light through to produce brighter and sharper fringes. So, as in Young's double slit experiment, the first order bright fringe is obtained when the path difference between adjacent slits is one wavelength. Okay, and we've seen this diagram before, this little triangle here, and that's the path difference is that little tiny part there, and that's one wavelength. And we've got a very tiny, tiny angle, and we'll call that theta 1. That's for our first bright uh, first bright fringe, so the first maximum after the minimum. Sorry, first maximum after the central maximum. Okay, so we've got that triangle there. Try and draw that. So we've got a wavelength there, lowercase d, and that's theta 1, angle 1, because it's the difference between paths for the first maximum. Okay, so we've got central maximum, minimum, and then first maximum. Okay, so that is one wavelength path difference gives us our first maxima. So looking at that triangle, sine theta 1, sine equals opposite over hypotenuse, so wavelength over lowercase t, distance between slits. So we can rearrange that and we can find the wavelength is the distance between slits times by sine theta 1. So that's the first maxima. The second order bright fringe is obtained when the path difference between the adjacent slits is two wavelengths. So instead of the above triangle, we now have two wavelengths there. We still have that same d there, and we've got a new angle theta 2 there. Okay, so sine theta 2 is 2 lambda over lowercase d. So rearranging it, 2 lambda is lowercase d times by sine theta 2. Okay, and so on and so on. So if you had the third order bright fringe, it would be 3 wavelengths difference. So it would be sine theta 3 would be 3 wavelengths over lowercase d. So for the general formula for the nth order spectrum is n, so 1, 2, 3, 4, 5 times the wavelength equals d times sine theta n. So for the third order bright fringe, 3 wavelengths would be d times sine the angle at which we've got the third order fringe. Now, if we look at the similar triangle again, so remember when we had the Young's double slit, so instead of a double slit, we'll say we've got a diffraction grating, so it's just basically lots and lots of slits. And we have a screen over here. And this is our central line where there would be a central maximum, so maximum there. Then we'd have a series of minima, then maxima, then minima, then maxima, then minima, then maxima, etc., etc., etc. Okay, so that's max, first order max, second order max, third order max, etc., etc. Okay, and we had this triangle that we said is a similar triangle, so we can say that the angles are the same as these little triangles here. So if we were looking for the third order max, then the triangle would be that. So including the central line and including this. So that would be my theta 3, because that's the angle to the third max. Okay, so that is you can apply that to this equation here, or generally this equation here. So if we wanted to say find the wavelength and we had the second, we're using the second maximum, then we'd use this triangle here, and that would be theta 2, that angle, theta 2. And similarly, let's go for red. If we just had the first maximum, we'd use this triangle here. And that would be our θ1, the first maximum. So you can see there, that's how you'd use this equation more often than using the small triangles. So you'd use, say, for example, we looked at the third one. Say if we were looking at, let me go back to my green actually. We're looking at the green triangle, so we were measuring to the second maximum. So we'd know that we could measure basically any of these lengths using a ruler or a measuring tape, and you could work out what the angle would be. Or you could even sometimes directly measure the angle with a protractor, depending on how big the maximum and minimum spread is. And you would say, so for the second maximum, you say 2 times the wavelength equals d, which is the distance between the slits, which you are normally told in a diffraction grating. Your diffraction grating will either tell you the distance between the slits, or it will tell you how many slits there are per millimeter. So it might say 100 lines per millimeter, and I'll tell you how to work out the distance between the slits from that. What you would do is you just do 1 millimeter divided by 100. Okay, if there are 200 lines per millimeter, it'd be 1 millimeter divided by 200. So you'd find that out from, you'd just be given the d, or you'd be given something to work out the d, and then times by sine theta 2, which would be that angle there. Okay, so we're going to do an example of this just now. Monochromatic light from a laser is passed through a grating with a 200 lines per millimeter gap. The third bright fringe is found to be 21 degrees from the central axis, so that's our theta n. So first of all, we want to calculate the spacing of the lines in the diffraction grating. So our diffraction grating, we're told, has 200 lines per millimeter. So to find the spacing between those lines, if we have 200 lines per millimeter, try that again. So if we've got 200 lines per millimeter, that means the distance between each line, so lowercase d because that's the distance between slits, is going to be 1 millimeter, so 0.001 meter, divided by 200. So 5 times 10 to the minus 6 meters, because we want it in meters. So that's how you find the spacing between lines in a diffraction grating. So if it's 300 lines per millimeter, it would be 1 millimeter in meters divided by 300. So 0.001 divided by 300. Part B, calculate the wavelength of the laser light. So it's a diffraction grating. So we know that the equation for the diffraction gratings is n times wavelength equals d times by sine of theta n. So we are told in the question that it's the third bright fringe at 21 degrees. So n is 3 times the wavelength equals d, which is what we found out in part A. So 5 times 10 to the minus 6 times by sine of the angle at the third bright fringe, which is 21. So the answer to that, the wavelength is 5 times 10 to the minus 6 times sine 21 divided by 3, which comes to 5.97 times 10 to the minus 7 meters. Okay, so if it's a diffraction grating, you use the equation n lambda equals d sine theta n. So there's an example here of a practical that I'll show you the video of the practical. So we've got a laser going through a diffraction grating. So to find the wavelength of the laser using this, what you need to do is the following. So mark the point where the zero order beam hits the screen. So that's where your first maxima would be. Mark the point where the first order maximum beam hits screen B. So basically that's our zeroth order maximum, is right where there's zero difference. And that's our next maximum is at B. So then you need to measure the distance AB using a meter stick. Then measure the distance BC using a meter stick. Or a measuring tape, depending on how big it is. And read the number of lines per millimeter from the diffraction grating. So what you would get is a triangle where that would be BC that you've measured. That would be AB that you've measured. You can find the angle using trigonometry. So the angle would be, well, sine of the angle would be AB over BC, opposite over hypotenuse. So you'll have AB and you'll have BC from the experiment. Your number of lines per millimeter from the diffraction grating would be, so to find lowercase d, your diffraction grating would say 100 lines per millimeter, or say for example 300 lines per millimeter. To find your distance between the slits, you'd have to do 1 millimeter divided by 300. So if it was a 300 lines per millimeter, your distance between slits would be 3 times 10 to the minus 6 meters. Okay, so if that was a 300 lines per millimeter diffraction grating, your lowercase d would be 3 times 10 to the minus 6. So to find the wavelength, you'd use the diffraction grating equation. So n times wavelength equals d times sine theta n. So you're just looking at the first order maximum. So it would be 1 times the wavelength would be d. So in this case, if we use that one, it'd be 3 times 10 to the minus 6 times by sine theta. And you could find your wavelength from that because you know sine theta because you know AB and you know BC because you've measured them. So that's how you would find the wavelength from that. I will send you a video of that so you can watch it in action.